Welcome back to the Biosystems Analysis and Modeling series. In the last module, we looked at some simple population models, exploring how to represent these conceptually and mathematically. In this module, we begin to explore systems consisting of more than one component. Typically, the systems we examine will be nonlinear, and we will explore the mathematical representation and analysis of these systems. Upon completing this module, you will be able to, first, represent coupled mechanistic models in systems diagrams in mathematics. Second, understand equilibrium points, how to identify them, and implications for system behavior. And third, you'll be able to interpret state space diagrams describing relationships between state variables in a system. In this module, we will be transitioning from models of a single state variable to models containing multiple interacting state variables and venturing into the realm of true systems modeling. The next step is to look at systems consisting of multiple coupled state variables. Because our models will have multiple state variables, they will get expressed mathematically as systems of ordinary differential equations, one for each state variable in our model. We will take a similar approach to what we have previously done in conceptualizing a model and then translating that description into the corresponding mathematics. Because we will need to be able to solve systems of coupled ordinary differential equations, it will be rare indeed to find analytic closed-form solutions to any of these models, and we are firmly in the realm of numerical methods for solving these models. Fortunately, Python and most other programming languages have libraries that make solving these models reasonably straightforward. The first model we will look at in this section looks at a population coupled with a non-renewable resource. Unlike the models we've looked at previously, this is a system of two state variables, a population P and a resource R. The resource is consumed by the population at a constant per capita rate and is not renewed. The population grows according to exponential growth and experiences mortality at a per capita rate that is inversely proportional to the remaining resource base in any given time. Because the system contains two state variables, our model will consist of two coupled differential equations, one describing the dynamics of the population, one describing the dynamics of the resource base. For the population P, our rate equation includes an exponential growth term and a mortality term that includes a per capita rate that scales with the inverse of the existing resource base. For tracking our resource, our rate equation includes a loss via consumption of the resource expressed as a constant per capita rate. Between population and resource, we fully captured the dynamics of this system. This is a nonlinear system. Why? Remember, a nonlinear system is a system whose rate equations contain at least one nonlinear term. The exponential growth term b times p is linear, as is the consumption term c times p. However, the mortality term r times p over r0 is not linear because of the coupled terms r times p, the product of our two state variables. This is one point at which this system is coupled. The dynamics of P depend on R. Further, the dynamics of R depend on P via the coupling term C times P. But what makes this system nonlinear is the presence of the R times P term describing the mortality of P. Here's the systems diagram for this system. Note the two state variables, population and resource, and associated flow, including birth, mortality, and consumption. Can you identify the feedback loops in this system? There are three. The first of these is the feedback loop around the birth process. The population size affects the overall rate of growth, which in turn affects population size. This is a positive feedback loop driving growth of the system. We can see this in the mathematics as well in the b times p term. The positive sign on this term indicates that it is a positive or reinforcing feedback. The second feedback loop involves the mortality process. It is a negative or stabilizing feedback loop. It balances the exponential growth in the system, providing stability to the system. Again, we can see this in the mathematics as well, as indicated by the negative sign on the mortality term. Finally, there is a more complex feedback loop related to resource consumption. This is a negative feedback loop where the resource influences population size via mortality, which in turn influences resource levels via consumption. The negative consumption term in the resource rate equation is another indication that it is a negative feedback. What type of dynamic behavior would you expect from this system? Let's look at some model results for three cases: a base or reference case, a reduced per capita growth rate case, cutting the per capita growth rate constant in half compared to the reference case, and a third case that reduces the per capita consumption rate constant in half compared to the reference case. We will run the model for 100 time units. But before we look at results, here's a thought experiment. Which of the two parameters, per capita growth rate or per capita consumption rate, do you think has a bigger influence on maximizing the lifespan of the population? Our model scenarios should allow us to shed some light on this question. Here's the model output. These are traces through time of the modeled population in resource levels. In all cases, the population increases initially, but ultimately crashes as the resource becomes depleted. It appears from our model behavior that reducing the per capita consumption rate is a more useful strategy than lowering the per capita birth rates for maximizing the population's lifespan. As we look at model output for a given set of inputs and parameter settings, we should ask ourselves, what are some of the assumptions that are implicit in the model? Under what circumstances would you consider this model to be useful? What might cause you to be skeptical of this model? Next, we'll take a different lens through which we might want to look at our system, a state space diagram. A state space diagram is simply a plot of one of our state variables against another state variable, with the trace on the plot indicating the pathway of the system through time. Each dimension in our state space is a state variable in our system. In this plot, the resource level is on the x-axis, and the population level is on the y-axis. The traces show the trajectory of the system through state space for each of the three cases. Initially, at time 0, our system starts at the right-hand side of the state space. This represents the initial conditions that we place our model in. For the base case, the system follows the red path. For the reduced per capita growth rate case, the system follows the green path through time. And finally, for the reduced per capita consumption rate case, the system follows the blue path through time. State space diagrams can be a useful tool for understanding system behavior and are a good thing to keep in our tool belt. We'll see some more examples a bit later in this module about how these systems, state space diagrams are used. But before we move on, let's ask ourselves a question. Where did the system end up in each of our three cases? It appears in all cases the population always reached and stayed at 0. It further appears that even though populations hit 0, there were multiple different outcomes for resources at the end of the simulation, when the system has reached equilibrium, or what we term steady state. When at an equilibrium point, the system does not change, and it does not move in state space. This is an important characteristic of a system that we'll be exploring throughout this module. Equilibrium points represent locations in state space that the system is at steady state. Mathematically, these points occur where the state equations describing system dynamics are equal to 0, meaning there's no change in the system at these locations in state space. In other words, if the system finds itself at an equilibrium point, it will stay at that equilibrium point until the system is perturbed. We find these equilibrium points by setting the differential equations describing rates of change of the state variables to 0 and finding solutions to the model at these points. For example, in the overshoot and collapse example, equilibrium points exist when C is equal to 0 or P is equal to 0, implying no consumption and hence no change in the resource level. And the per capita birth rate is equal to the per capita mortality rate, implying no net change in the population. Under these conditions, the system will be at steady state. We can easily identify these points by solving the state equations at steady state. Keep in mind that for nonlinear systems, there may be 0 or more solutions to the steady-state equations, and therefore 0 or more equilibrium points. The next system we look at focuses on the interactions between a predator population and a prey population, for example, foxes and hares. The conceptual model makes several assumptions. First, the population of predators increases through growth, with the growth rate dependent on the rate of predation. Second, the rate of predation is proportional to the amount of prey and the amount of predators available to eat them. Third, the predator population declines due to natural mortality at a rate proportional to the population size. And finally, the prey, in contrast to the predators, reproduce at a rate proportional to their population size and are removed only by predation. Translating the conceptual model into mathematics, let's start with the prey population H. Our conceptual model states that the prey population grows at a rate proportional to the population size, which is exponential growth. Further, the conceptual model states that the prey mortality is from predation alone. Examining the predation process, our conceptual model indicates that the rate of predation is proportional to the amount of prey and the amount of predators. In other words, predation is the result of an interaction between a predator and a prey and requires both to be present. We indicate this interaction with a multiplicative relationship. For the predator population, growth is proportional to the rate of predation, and mortality losses are proportional to the population size. This captures all of the processes stated in the conceptual model. Now that we have a model, what are some of the questions we might be able to address? For example, under what circumstances might this model be reasonable? To answer this, we want to take a close look at the assumptions embedded in the model. For example, the conceptual model doesn't consider immigration into or immigration out of either population. If these processes are important in the real-world system being modeled, then this model may not be appropriate. Second, how would we solve this model? Is the model nonlinear? The answer is yes, because of the two terms involving h times p. This suggests an analytical solution is unlikely, and we will need a numerical method. We will be looking at methods for solving this system in a later module. Third, under what circumstances would the populations be in equilibrium? We can answer this by setting the differential equations to 0 and solving for h and p values. Try this on your own. For any given set of model parameters RH, RP, A, and B, you should find two equilibrium solutions. One of these is 0, 0 for H and P at the origin of the state diagram. The other is dependent on the model parameters. Here, we see the time series traces on the left-hand chart and the state space diagram on the right-hand chart for the predator-prey system. Looking first at the time series traces on the left, we see that for both predator and prey, each oscillates periodically through time. As rabbit populations increase, foxes increase as well due to the increased availability of prey. This in turn causes a reduction in the rabbit population, which in turn leads to a reduced predation and therefore reduced fox populations. With reduced fox populations, the rabbit population can rebound and the cycle starts over again. Let's turn our attention to the state space plot on the right. The arrows on this diagram indicate the direction the system will move if it is at a particular location in state space. The orange traces are the system trajectories for various initial population sizes. This view highlights some interesting aspects of this model. First, we can readily see the oscillatory nature of the system. Once initially placed in state space, the system will cycle around a particular pathway forever. It never reaches an equilibrium point unless the system initially starts at that equilibrium point, in which case it will stay there forever. Second, the equilibrium points are pretty apparent in this view. One is located at the center of the cycles at location 2010 in the state space. One can think of this location as a cycle with the radius of the cycle reduced to 0. A second equilibrium point is located at the origin. If the system starts with no predators and no prey, not much is going to happen. Let's consider whether these equilibrium points are stable or unstable. A stable equilibrium point is one for which, if we perturb the system when it is at the equilibrium point, it will return to that point. An unstable equilibrium, in contrast, is one in which a perturbation will result in movement away from the equilibrium point. Let's consider the equilibrium point at 2010 first. This point is a weak attractor. As the system moves through state space, it is bending towards this point, but the attractor is not strong enough to pull the system all the way to equilibrium, analogous to the moon circling the Earth. So what would happen if the system started at this equilibrium point, but then we perturb the system to, say, 30 rabbits and 15 foxes? Meaning we're going to add more rabbits and foxes to the system, and it will no longer be in an equilibrium state. Would it return to equilibrium at that point? The answer is no. We can see from the state space diagram that the system would not return to the equilibrium point, which defines the point as an unstable equilibrium point. Next, let's consider the second equilibrium point at the origin, where there are no foxes and no rabbits. What happens if we perturb the system by adding some rabbits? If we examine the blue arrows on the diagram, or the rate equations, we see that the system will move away from the equilibrium point. Rabbits will grow exponentially in the absence of predators. However, if instead we add only foxes and no rabbits, the fox population will return to zero as a result of the mortality with no offsetting growth. If we add both rabbits and foxes, the system will assume a new trajectory through state space and will not return to equilibrium. Hence, the equilibrium point at the origin is both stable and unstable depending on the nature of the perturbation. Stable equilibrium points are important when designing a system. Generally, we want our designs to operate near a stable equilibrium point that is also an attractor. This allows the system to be resilient to perturbations and continue to function in the face of these perturbations. Finally, let's look at one more model, also originally developed by Lotka and Volterra, this one examining competition between two species. The conceptual model is that in the absence of competition, populations grow according to logistic growth, as we have seen earlier, with the population size constrained by the carrying capacity. In the Lotka-Volterra competition model, we will modify this assumption a bit, focusing on the carrying capacity concept. First, we will extend the logistic growth model to encompass two species, resulting in two state equations, one describing the dynamics of each species. Further, we will introduce the concept of competition as an additional reduction in growth rate, reducing it by a factor described by the product of the population size of the competitor species and the competitiveness of the competitor species, captured by the model parameter A12 above. The factor measures the competitive effect of the competitor species on the target species, with higher values indicating a stronger competitor. We apply this concept to both species, resulting in the Lotka-Volterra competition model shown here. Let's examine this model from the perspective of equilibria. As before, we can identify equilibrium points by setting our state equations to zero and solving the resulting algebra for state values that satisfy the equilibria criteria. The equilibria point is at 0, 0. This is a trivial case where the population is zero in both species. In this case, the system is at equilibrium, but it is not a very interesting case. We can also see, however, that additional equilibrium exists for this model. In fact, the equilibria occur along a line rather than just a point. These models carve up state space into regions of behavior. The state space perspective can be useful for understanding the behavior of a system. In this state space, we will plot the abundance of species 1 versus the abundance of species 2, with species 1 on the x-axis and species 2 on the y-axis. Each point in a state space graph represents a combination of abundances of the two species. For each species, we can plot the zero isocline. the equilibrium lines identified on the previous slide. If the system reaches a point on the zero isocline, it will stay there unless the system is perturbed. At any given point along, for example, species 1's zero isocline represents a combination of abundances of the two species where the species 1 population does not increase or decrease. Note that the zero isocline divides each graph into two parts. Below and to the left of the isocline, the population size increases because of the combined abundances of both species are less than the carrying capacity of the one. While above and to the right, the population size decreases because of the combined abundances are greater than the carrying capacity. For the graph on the left showing the isocline of species 1, we can see that the isocline intersects the graph on the x-axis when N1 reaches its carrying capacity K1 and no individuals of species 2 are present. The isocline intersects the graph on the y-axis at K1 over A12 when the carrying capacity of species 1 is filled by the equivalent number of individuals of species 2 and no individuals of species 1 are present. The intersections of the isocline for species 2 are essentially the same, but on different axes. These two graphs illustrate what happens to a population when it is below or above its zero isocline, but they only account for one isocline at a time. Next, we will look at both species zero isoclines together and illustrate the possible outcomes of interspecific competition depending on where each species isocline lies in relationship to the other. We can imagine a surface of starting points in state space, and for any of the starting points not on an equilibrium point, the system will move along some trajectory towards any attractors in the state space. Often these attractors are stable equilibrium points, or lines, in the case of the Lockable-Volterra model. One can further imagine the state space as a surface on which the system moves. Here we see some possible cases when we examine the two zero isoclines simultaneously. Shown on these two plots are the zero isoclines for the populations N1 and N2, shown in blue and red respectively, and the flow path of the system through state space when out of equilibrium, shown by the arrows, which indicate the direction and speed of the system will move towards a stable equilibrium state, the closest attractor in state space. Keep in mind that in nonlinear models there can be multiple attractors in state space. Why do we care about any of this? Because systems like to be in stable equilibrium states, but resilient systems also like to live in strong attractors. That means when the system is perturbed, we generally want it to return to its former equilibrium point. This is fundamental to design. If we want to design a resilient system, it should be designed to operate near an equilibrium point, and that equilibrium point should be a strong attractor so that the system can handle perturbations. If we overload our bioreactor that cleans up wastewater because of a big storm event, for example, we want it to recover gracefully instead of it being attracted to some other equilibrium point, for example, dead. State space analysis provides a useful method for identifying equilibrium points and the basins of attraction around those equilibrium points. To understand how to interpret the state space diagram for this problem, let's examine four possible cases, or scenarios, of model parameter combinations. The first scenario is one in which the isocline for species 1 is above and to the right of the isocline for species 2. For this case, there are two equilibrium points, one at the origin, both populations are 0, and we will ignore that one. But there's one that occurs on the x-axis at K1 as well. For any point in the lower left corner of the graph, meaning any combination of species abundances to the left of the red line, both the populations are below their respective isoclines and both increase. For any point in the upper right-hand corner of the graph, both species are above their respective isoclines and both decrease. For any point in between the two isoclines, species 1 is still below its isocline and increases, while species 2 is above its isocline and decreases. The joint movement of the two populations is down and to the right, so species 2 is driven to extinction and species 1 increases until it reaches its carrying capacity, K1. The second scenario is the opposite of the first. The isocline of species 2 is above and to the right of the isocline for species 1. This graph can be interpreted in much the same way as the previous one, except that the joint trajectory of the two populations, when starting in between the isoclines, is up and to the left. In this case, species 2 always outcompetes species 1, and species 1 is competitively excluded by species 2. In the third scenario, the isoclines of the two species cross one another. Here, the carrying capacity of species 1 is higher than the carrying capacity of species 2 divided by the species 2 competition coefficient, and the carrying capacity of species 2 is higher than the carrying capacity of species 1 divided by the species 1 competition coefficient. In this case, there is an unstable equilibrium point indicated by the open circle where the isolines intersect. For initial populations above or below the two isoclines, the system will move along a pathway towards exclusion of one species. Which species is dependent on the starting population sizes. For the points above the red line, the species 2 isocline, and below the blue line, the species 1 isocline, the outcome is the same as in the first scenario, competitive exclusion of species 2 by species 1. On the other hand, for points above the blue line, and below the red line, species 2 will competitively exclude species 1. The two stable equilibrium points are again represented by filled circles. In this scenario, the outcome depends on the initial abundance of the two species. Finally, in the fourth scenario, we can see that the isoclines cross one another, forming a stable equilibrium point. But in this case, both species' carrying capacities are lower than the other's carrying capacity divided by its competition coefficient. Again, below both isoclines, the populations increase, and above both isoclines, the populations decrease. In this case, however, when the populations of two species are between their isoclines, their joint trajectories always head towards the intersection of the isoclines. Rather than outcompeting one another, the two species are able to coexist at this stable equilibrium point at the green circle. This is the outcome regardless of the initial conditions the system experiences. The Lotka-Volterra model of interspecific competition has been a useful starting point for ecologists thinking about the outcome of competitive interactions between species. The assumptions of the model, for example, there can be no migration, and the carrying capacities and competition coefficients of both species are constants, are sometimes not realistic, but are useful simplifications. A variety of factors not included in the model can affect the outcome of competitive interactions by affecting the dynamics of one or both populations. Environmental change, disease, and chance are just a few of these factors. So, to recap, in this module, we started looking at systems with multiple interacting components from the points of view of representation and analysis. We saw that we can apply the same approach we use for single component systems to represent multiple component systems. Representing systems dynamics as differential equations is an appropriate choice for multiple component models. Second, we saw that state spaces can provide a useful lens on systems dynamics. By describing how a system will move through state space, we have a useful way to understand system behavior. Third, equilibrium points are useful to identify when designing systems. They may be stable or unstable. Stable equilibrium points tend to be system attractors. We can identify these points easily by setting our model differential equations to 0 and solving for the steady-state values of our state variables. Fourth, successful systems designs operate near stable equilibrium points, and equilibrium points that are strong attractors lead to resilient designs. This is important to keep in mind when designing systems that are able to accommodate perturbations and other types of disturbances. Finally, we recognize that we are quickly leaving the realm of analytical solutions, and we will need methods for solving the resulting systems of differential equations that are describing these models.